Now let's talk about covariance and correlation. Covariance and correlation are two numbers that quantify the direction and strength of the linear relationship. This is important, the linear relationship between two random variables. Okay? The correlation can be thought as a standardized version of covariance. The ranges for the covariance is any value in the real line, so it's between minus infinity to infinite, and the correlation, that is raw, of two random variables could be 1 or minus 1, and it's between those two numbers, minus 1 and 1. To interpret the magnitude, the covariance magnitude depends on the units of x and y, and is thus not especially informative. On the other hand, a larger value for the correlation indicates a stronger linear relationship. Remember that it's always linear relationship between x and y. To interpret the sign, if larger values of x tend to be associated with larger values of y, then the covariance and correlation are positive. Right? Larger values of x tends to be larger values of y, then it's positive. But on the other hand, if larger values of x tends to be associated with smaller values of y, then the covariance and correlation are negative. The relationship to independence. If the covariance of two random variables is equal to 0, we call x and y uncorrelated. Okay? We are going to see that covariance and correlation are related. But if x and y are independent, they are uncorrelated. So that means if they are independent, that implies that they are uncorrelated. Independence implies uncorrelation. The converse is not necessarily true. If x and y being uncorrelated only means they have no linear relationship. Okay? Let's see these visualizations. So for example, if x and y, let's consider we have contour plots. We have values that move around those values, and it seems there are positive. Here we can see that there is a positive covariance and correlation. Why? Because larger values of x tends to have larger values of y. But on the other case, for example, if we have something like this, larger values of x tend to have smaller values of y. So here we have negative covariance and correlation. We have more visualizations for correlation. So here, for example, this value 1 is a perfect linear relationship between two random variables. Here, for example, this 0, that means there are no linear relationship, but these, for example, these values over here, all of these represents a correlation equal to 0, but that means that not necessarily means there are no relationship between those two random variables. The linear relationship is not exist, but could be another type of relationship. So this -1 says that there is a perfect linear relationship, negative relationship, and so on. The formulas. Okay. The formula for covariance and correlation is the same for both cases, discrete and continuous. The covariance of x and y is the expected value of x minus expected value of x times y minus its expected value. And if we do some algebra here, is the expected value of the product of the random variables minus expected value of x times the expected value of y. The formula for the correlation of x and y, this pro, is the covariance of x and y over the standard deviation of x times the standard deviation of y over the product of the standard deviations. To calculate the expected value rule, we already have discussed this. We can use this to calculate this expected value of x times y, and we know that this is the double sum over x and y of this function. In this case, the function is x times y, so this is x times y times the probability of x and y times the joint PMF. Here we use the expected value rule to calculate this expected value of the product of the random variables, and it's going to be the double integral from minus infinity to infinity of x times y times the joint PDF. Okay, we have some properties here, so you can check them. They're very easy to remember. Basically, the covariance is commutative, so it's the same to calculate the covariance of x and y than the covariance of y and x. The covariance of the same random variable is the same variance. The covariance of x and a linear relationship of the other random variable is calculated like this. We have the formula for the covariance of one random variable and the sum of two other random variables, and we have a formula for the correlation. And the number 6 is one of the most important. The variance of the sum of two random variables in general is the sum of the two variants. Well, here is minus or plus. So plus 2 times the covariance of x and y. Okay, this is the most important property here, one of the most important. Number 7, if x and y are uncorrelated, so we already saw that in the case of uncorrelation, this covariance is 0, so that means the variance of the sum is variance of x plus variance of y. And if x and y are uncorrelated, the expected value of x times y is the expected value, or is the product of the expected values. Okay, let's see this example, and with this we finish. Consider x and y with joint PMF given below, and we have to find the correlation of x and y. So the correlation, this row here, it's like this, is the covariance of x and y over the standard deviation. So we have to find the covariance first. Let's do this. The covariance of x and y is, using the formula, is the expected value of x times y minus the expected value of x times the expected value of y, right? What is this first expected value? Well, this expected value, using the formula, is the product of the two values times the joint PDF, so it's going to be 1 times 3 times the joint PMF, in this case is 0.3, plus the other case is 1 times 4 times 0.1 plus 2, this 2 times 3 times the joint PMF, plus 2 multiplied by 4 multiplied by the joint PMF, that is 0. That is the expected value of the product of the two random variables, x and y. And we have to do minus the expected value of x. The expected value of x is going to be, we have to calculate the marginal. So remember, we have to calculate the marginal here. It's going to be 0 0.4, 0 0.6. This is the marginal for x. And we have to sum here. This is 0 0.1, 0 0.2. This is the marginal for y, right? So the marginal for x is that. So we have that the expected value is 1 times its probability, that is 0 0.4, plus 2 multiplied by its probability, that is 0 0.6, right? And we have to multiply that by the expected value of y, and that expected value, so we already have the marginal here. This is the marginal of y, is 3 times 0 0.9 plus 4 multiplied by 0 0.1. And this is equal, if we do this algebra here, these multiplications, where the first one, the expected value of x times y, this green calculation here is 4.9 minus the expected value of x is 1.6 times the expected value of y, that is 3.1. And that is finally minus 0.06. Okay, that is the covariance of x and y. And we have to find the correlation. So we need the covariance, we already have that, but we need the standard deviation, and the standard deviation of x and the standard deviation of y. So that means we have to calculate the variance. So the variance of x, remember the formula, is the expected value of x squared minus the expected value of x to the square. And we have to calculate this expected value because we already know this value, that is 1.6. So to calculate this expected value, we use the expected value rule. That is, we take the values of x to the square, that is 1 to the square times its probability, that is 0.4, this value here, plus 2 squared times its probability, 0.6, minus this 1.6 to the square, that is the expected value of x, and this is around 0.24. Okay, to calculate the variance of y is the same, is like the same. I'm really tired. The expected value of y squared minus the square of expected value of y. This expected value, we have to calculate it, so it's 3 to the square times 0.9, so it's 3 squared times 0.9, plus the other value of y is 4 to the square, and multiplied by its probability, that is 0.1, minus the expected value of y to the square, that is 3.1 square, and this is 0.09. And finally, the correlation here, the correlation between those two values, two random variables, sorry, is the covariance, that is minus 0.06 over the standard deviation of x, that is the square root of this, because this is the variance, 0.24, times the square root of the variance of y, that is 0.09. And if we calculate this, is approximately minus 0.3. So it's a negative correlation here. That it means larger values of x are associated with smaller values of y.